All right, everyone. Warm welcome to chapter number 3, Modeling in R. And after having recorded the videos in German in the last semester with Jan, we now decided to make the class as inclusive as possible. And we are recording English lecture videos this semester. So please don't be too harsh if I'm stuttering or making some mistakes. I'm trying to do my best to do that. And this session 3, captioned Modeling in R, where we will look at how to model things in R, estimate and visualize statistical models. I want to kick it off with a big thank you to Carolina Hensch, a colleague of Jan and me, who provided me with some great materials that I have partially used to create this lecture. All right, as an agenda for the entire session or set of videos, I'm doing a quick intro right now. Then we will look at linear regression and logistic regression, two very important model types in more detail. And then I will talk a little bit about other models, really short, because we don't have the time and the capacities for that, unfortunately. Give some important remarks, really important, before we jump into modeling in R. All right, let's talk about statistical models in general. Our basic, very basic setup is that we have an interest in a relation between two or more variables. For example, we have the number of children, and we would like to find out what's the relation between the number of children that an individual has and the individual's life satisfaction. In this bivariate case, so two variables, we know we can calculate, for example, a correlation coefficient, but how are we doing that if we have a more complex setting? We don't only want to understand the effect or the relation of number of children on life satisfaction, but we really want to study life satisfaction. What is the determinant of life satisfaction? Could income have an influence? How about health, perceived health, marital status? So are married people maybe more happy or even more unhappy? We would like to know that, and here the correlation coefficients and so on come to their end really quickly. So we need a statistical modeling. So that is the big use case. We want to understand the multivariate relationship of some concepts, and we call these the outcome variable. We call the dependent variable. The variable that we would like to understand the most, and the other variables, the explanatory variables, we call the independent variables. All right, depending on variable type, model type, and so on, it's more or less straightforward to interpret these models, and we are going to look at the first and foremost and also most important model, the linear regression first. I will give a really brief theoretical intro, or shortened theory. Please, if you didn't touch upon this in a statistics class, take a look at a statistics book, something like that. We don't have the capacities to fully go into detail on the theory, but it's important. I saw that many of you have some knowledge about it already, but those who don't, please don't only use this video to understand what are the statistical, theoretical, the theoretical ground for linear regression. In general, the application that we have is to model the relation. Let me take my laser pointer. To model the relation of a set of independent variables, we call them x, as I previously showed you the example, on a dependent variable called y. Let's ignore the bottom part first. It can be done under certain assumptions that need to hold for linear regression to be an applicable modeling method. These are the 5 assumptions. So the first is linearity. It's obviously called a linear regression. So what we need to assume is a linear relationship between x and y, so our independent and our dependent variables. It means if this relationship is not linear, if we assume it to be, for example, in a logistic form, we know that linear regression is not the right model to choose here. Then second assumption is the independence, and more specifically the independence of observations. So certain observations, for example, if observations are people or surveying people, they need to be independent of each other. So for example, if someone takes a survey of me and of Jan and I shouldn't interfere between these two time points and be able to talk to each other. So it should be totally independent, all the observations. Third assumption would be the normality. So residuals, I hope many of you noticed, is the difference between what the model would estimate as an outcome and the observed outcome should be normally distributed around the mean of 0. So that means that our residuals scatter around in a normal distribution around 0. Then fourth assumption is the homoscedasticity, meaning that the variance of residuals is constant across all levels of, IVs means independent variables. So we want our residuals to be constant and normally distributed and not have some weird patterns, because then we know that something is maybe an explanatory variable is missing, or we have some nonlinear patterns. And then fifth and last assumption is the assumption of no multicollinearity, which means that the independent variables are not perfectly correlated with each other. So there might be in theory, it might be that two variables have a perfect correlation, and if we have that violates this assumption of linear regressions. And then if we estimate one of these models, we will get a resulting model in the following, let's say, mathematical notation form. So our y, our outcome, our dependent variable, equals beta 0, which is called the intercept in a linear regression. In German der y-Achsenabschnitt. Plus we get these coefficients, beta 1, beta 2, and so on. For each of our independent variables, for example, x1 could be an independent variable. Let's say this is the number of children. We get a coefficient for each of the independent variables, which can be used to interpret the relationship between an independent variable on its respective dependent variable in this model. And the sum of this right side of the equation is then what our model would predict or estimate for our dependent variable. If we run a linear regression in R, we always have to assign the model to some object. Here I call it model, and the function is really, really easy. I won't go into too much detail with respect to the code, because we will do that in R later. But LM is the function. It stands for linear model. Then you have the dependent variable. In this case, I used the Boston housing dataset. Our dependent variable is the price of houses in Boston in thousands of dollars. Then you have the tilde sign. It's just is like a separator between the dependent and the independent variables. And then you just sum the independent variables with pluses in between. So here we have some independent variables, and at the end you specify which data was used, and here we use the df data frame. If you do that, you run the model and you give yourself, or you take as output the summary of the model, you will get this, maybe at first glance not straightforward and maybe messy output, but there's a bunch of information for us. So here, let's ignore the upper part. Here's how our model was calculated. Then we get to the coefficients, which are most important. We see our intercept is an estimate of 17.7. Intercept is sometimes difficult to interpret, so let's look better at our independent variables. For each variable, we get a coefficient. For example, in the mathematical notation, this would be beta 1, beta 2, and so on. We get a standard error, and we get t-value, and actually we get these stars, which indicate the significance of our coefficients. So if a coefficient has the more stars, the more significant we can say. And if you don't see any stars, like here for the variable crime, which is the crime rate, and NOx, which is the, I think, some kind of air pollution, we can see that these coefficients are insignificant. So they don't have a significant impact on the price of a house in Boston in our model. All the other coefficients are highly significant. And then what else is really important, what I want to take away here is the multiple R squared or the R squared metric. I hope many of you know it. An R squared of, let's say 0.7, let's round this, means that 70% of the variance of our dependent variable price of the housing is explained by our model. So it obviously it can range between 0 and 1, and the higher your R squared, the better your model seems to be. You will always, of course, want the highest R squared as possible. Then, in addition, I hope that many of you know this as well, we can estimate confidence intervals. So for each coefficient, let's take the chess independent variable, which is a binary variable which says, or which can take the values 0 and 1, and it's 1 if it's on one side of the river and 0 if it's on the other side of the river, if I understand the dataset correctly. And we have our upper and lower boundaries of the confidence interval. So for this variable, our coefficient, which is highly significant, ranges from is 3.5, and the confidence interval ranges from 1.7 to 5.3, which means if we would repeat our model estimation 100 times, because this is the 95% confidence interval, the true parameter, the population parameter, would be included in this confidence interval 95 times. So that means we would always like to have as small as possible confidence intervals to make more bold statements about our regression coefficient. Here again are the upper and lower boundaries for our confidence intervals. I just wanted to show this to you because with a package called Stargazer, we can create nicer outputs of the regression coefficients and also the confidence intervals. This is how it can be done in base R with the confidence interval confint function. If we then try to visualize our model results, first and foremost, I think it's a really nice and important plot. We can do a coefficient plot, which gives you the value for each of the regression coefficients with its respective confidence interval around here. So previously let's go back, that the regression coefficients for crime and the air pollution were non-significant. And this can actually be seen in this coefficient plot as well, because for both, the confidence intervals overlap with 0. And if they overlap with 0, we can say that they are not significantly different from 0. And something to be significant, we actually mean that it's significantly different from 0. We can say that for all of the other regression coefficients. And the smaller the confidence intervals, the better we feel about the interpretation of the exact coefficient. So the coefficient plot is really nice to see also whether a independent variable has a positive or a negative effect on the price. So let's say this variable has a positive value, Rm, which means that this variable has a positive effect on our on the price of houses. Everything that's around here, for example, air pollution has a negative effect, which means the higher the air pollution or the worse the air is, to loosely spoken, the lower the price gets of the houses. Another nice opportunity to visualize this is a residual plot. Sorry, I just lacked the word. A residual plot. The residuals, as I previously said, as the difference between the estimated or predicted value for the dependent variable versus the observation, given the set of independent variables. And of course, in a perfect model, we would strive for residuals 0, which means that our estimation of our model would always be perfect, but in reality, it never happens. So for our regression model here, we can see that the residuals are kind of scattered around 0. Maybe we are not perfectly confident that this should probably be normally distributed around 0. I previously said that this is one of the assumptions for linear regressions. But we kind of observe that it's not really normally distributed. Maybe it's not that so bad that we can't run linear regressions, but we should keep an eye on it. So this is pretty nice, these residual plots to check for the assumptions of linear regressions and just to understand where your prediction was off and where it was better. All right, this was a very short and probably incomplete introduction to linear regression. Unfortunately, it's a little bit out of our capacities and skills to explain this in a very complete and basic manner. But please look at some great introductions if you haven't already touched upon this in your Stats 1 or Stats 2 class or any other class. So that's for now for linear regression basics. We will look at linear regressions in R in one of the later videos, and there also understand how to interpret the regression coefficients. And in the next chapter, we will look at logistic regressions.